Section 2.11 is going to cover two main ideas, the first of which being implicit differentiation. And really truthfully, the second part being related rates. They're very similar. Related rates uses implicit differentiation. So we're going to break up this section into two videos. First one being, let's just talk about implicit differentiation. Okay, so just to get us primed, just to get us set, let's find the derivative of this function, but without using prime notation, no using y primes. Okay, so what would that look like? How do you do that? Well, let's remember the notation we had for writing derivative was dy dx. But what we could say is, if when we want to notate saying I want to do the derivative of this thing, I could write d dx of one side and then say do d dx of the other side. And that just means, hey, do the derivative of the left-hand side where x is my variable and do the derivative of the right-hand side where x is my variable. So when I do the derivative of y, what we're saying to ourselves is the y function is some function of x. There's some x's inside of it. So what we're going to do is at some later point in time, if we knew what that was, we could go ahead and do the derivative with respect to y. But until then, we're just going to write this as dy dx. And you'll notice over here on the right-hand side, we know what that stuff is. We see all of our x's. So the derivative of x squared would be 2, and then bring that down. Now, so you can see that as the chain rule part, right? What we do is we have this squared, right? So you bring that out to the front, leave the junk alone. Now do the derivative of the inside. And we've never actually written this before, but if you stop and think about it, you say it's the same idea as what we just did with the y. Now I'm doing the derivative of x. And so it's the derivative of x with respect to x. And the reason we've never written this is because what's dx divided by dx? Well, that's 1. So therefore, we leave that alone. Or it's just the derivative of x is 1. The derivative of x is itself, right? When you do the derivative of x, that is 1. So therefore, we would just write as a 1. So anyway, now we can continue that. So then the derivative of 5x would be 5 dx dx again. So that's just 1. And then the derivative of 2, which is 0. So therefore, what we're seeing here is dy dx equals 2x minus 5. All right, easy enough. So now let me walk you through this one and see if this is really sticking here. All right, so the derivative of 3x, all right, so dx of, let's write it out the first time before we really start doing the derivative in our head. Excuse me, it helps if I put my parenthesis in the right place. There we go, equals dx of 4. Okay, so when we do the derivative of the left-hand side, we absolutely could solve this for y. But what implicit differentiation does for us is it says, don't bother. We could go ahead and differentiate right now with the x's and the y's all mixed together, easy enough. And let's go ahead and do that. So when you do your derivatives, you break it into individual parts. So the derivative of 3x cubed would be 3, and then bring the 3 out to the front. So 3 times 3 times x squared dx dx, because the derivative of x, the chain rule part of it, the derivative of the inside is dx divided by dx, so that is 1, plus, now here's the fun part. Here's this part right here, right? So how do you do the derivative of something squared? Well, you bring the 2 out to the front, so it's going to be 4 times 2 times, leave the junk alone, and so it's just y to the first. But then we have to do the derivative of y, which is dy dx. So there's our implicit differentiation for the term here with the 4y squared. So then finally, the one that we always goof up, what is the derivative of 4? Well, 4 is a constant, so the derivative of a constant is 0. So finally here, our answer turns out to be what? 9x squared plus 8y dy dx, which is equal to 0. So the implicit differentiation now, you'll see we have y's floating around in our answer. And that's one of the I don't want to call it a negative, but it's one of the downsides to implicit differentiation, or one of the things is saying, all right, if I want to know what the derivative is, now I need x's and y's. So, and to make that a little more clear, what I'm going to say is now let's go ahead and solve for dy dx to make it a little more clear what I'm talking about here when I say we need x's and y's. So now kicks in just a little bit algebra, just standard, nothing too complicated here. We're going to go ahead and just say, all right, subtract 9x squared from one side, subtract 9x squared from the other side. And what would that give me here? That would leave me with 8y dy dx, which is equal to negative 9x squared. Now, to get dy dx by itself, we're going to have to go ahead and divide by 8y. So divide this side by 8y, which would therefore leave me with dy dx, which is equal to a negative 9x squared over 8y. And what we're seeing here in our answer, the final answer, we are now done. What we are seeing here is the derivative notation like we're more used to seeing it. This is just dy dx. This is saying the derivative of your y function with respect to x is equal to this equation over here. And what we're seeing is, notice there's x's and y's. So if you had someone out in the field and you said, I need the derivative, I want to find the derivative of this function, what you would have to be telling your employee or your scientist or whoever you have out in the field, I need an x value and a y value. You give me both of those things. You give me an ordered pair, and I can now tell you the derivative. I can now tell you its speed at that place. So the implicit differentiation allows us to do derivatives of things where we may not have been able to before, except now, when you get your derivative, you now need a little bit more information. I don't have just an x. I can't just say substitute an x, get out your slope. Now I have to know an x and a y, and I get out my slope. I hope that's making sense. So let's go ahead and look here. Let's look right here and kind of fill in here. So the big idea is, when would you want to use implicit differentiation? When is it most useful? And one of the really common uses is just when you can't solve for y, when it's too hard to get y by itself, or the function would become so cumbersome that it's just not worth it. You'd say, look, if I were to solve this thing for y, what would we be looking at? If we were solving for y, we would have, let's see, this would be 4y squared equals 4 minus 3x cubed. And then I could divide by 4, so this gives me y squared equals 4 minus 3x cubed divided by 4. Then I'm going to go ahead and do the square root of that, so that's going to give me plus or minus the square root of 4 minus 3x cubed divided by the square root of 4, which is 2. And so now doing this derivative, while it isn't terrible, it's just a little bit of chain rule, and you could do it, and it's actually kind of fun. What you could do is, when you do this derivative, you would see this derivative is the same as that. Once you then say, we know y is all this, so you could go ahead and sub all that stuff in for the y in the denominator, and it would give you the same derivative. But you may not care. You may not want to go through all that work. You say, look, this formula we have highlighted is way easy, and in the real world, all we need to do is we can go out and get x and y readings. There's no reason to make the formula so cumbersome and horrible. So don't. So I hope that's kind of making sense. So one application. There are a few different times we'll use implicit, but one of the key reasons we use it is just when you can't solve for y. It's just too hard. Okay, so go ahead, pause the video, try this problem, and see if the implicit differentiation is kind of sticking for you. And this next time, from here on out, I'm not going to do this whole d dx idea, and I'm going to kind of just, if that's not sticking with you, I'm going to give you an idea on how to I hate the word memorize, but you'll notice there's a pattern. So you can kind of work your way around it if that d dx notation's bothering you. So go ahead, pause the video, give it a shot. Okay, so here we go. When you're doing derivatives implicitly, whenever you're doing a derivative of x, or if you're doing it with respect to x, so if we're doing d dx, you do it just how you've always done derivatives, right? So we're going to bring the 3 out to the front, so that's 9x squared, and then the chain rule says the derivative of x is 1, the derivative of the junk's 1, so yeah, who needs it? Plus, now, whenever you're doing derivatives with y's, you're still doing it the good old-fashioned way. You just have to remember, whenever you do the derivative of y, well, so let's get there. So it's 2 times 4 makes 8, 8y. So now, whenever we're doing the derivative of y, it's always dy dx. Just like every problem you've done up to this point, when instead of writing y prime, you could have been writing dy dx. So this entire time, you've been using that rule. The derivative of y, when you say, hey, any function we're used to doing up to this point, when I say, hey, do the derivative, you've used that notation, or you've used that notation. So that's not changing. The derivative of y is dy dx. We did here the derivative of 4y squared. So we have chain rule. The 2 comes out to the front, and then leave the junk alone, times the derivative of the inside, the derivative of the junk. In this case, the derivative of the junk is y. So the derivative of y is dy dx. I hope that helps. Now, the derivative of 4 is 0. So now the next step, you must solve for dy dx, because that's how we write derivatives. It's always y prime or dy dx equals. So solve for dy dx. So here we go. Subtract the 9x squared over, maybe just a different color. So that's going to give us, that color didn't take. Let's try that one more time. 8y dy dx equals 0 minus 9x squared. All right. So then we're going to divide by 8y and see how easy the solving is. And I don't know why I just did 0 minus. Okay, it's been a long week. Okay, there we go. So notice how easy the solving is, because dy dx is multiplying this stuff. So all you do is divide by it, and you're done. So we're going to go ahead and say, all right, so that gives us dy dx is equal to 9x squared divided by 8y. All right, so if that's stuck, good. All right, so now here comes one that's a little bit harder. It's a little bit different, because now you'll notice we have x multiplying y, where in the previous problems we've always had x adding or subtracting with y, so there are separate terms. And our derivative rules say when you have terms that we need to do the derivative of, you treat them as separate problems. You just do the derivative of 3x cubed, you do the derivative of 4y squared, you do them totally separate. Well, what do you do when you have things multiplying? What derivative rule do we have for things that are multiplying? Product rule, right? And so you just have to recognize that when you have x and a y, that is 2 functions of x multiplying each other. We just can't solve for the one that's the y, but y is a function of x, so therefore it's a product rule. So here we go. Break up your product rule like however you've done it in the past. Break it up with parentheses or whatnot, and say, all right, the derivative of the first thing, the derivative of x is 1. Leave the other factor alone. And then the product rule says plus, it's adding. Now leave the first factor alone and do the derivative of the second. Well, what's the derivative of y to the 9th? Well, we're going to bring the 9 out to the front, subtract 1 from its exponent, right? And then times the derivative of the junk, the derivative of y is dy dx. And then the rest of the problem should be relatively straightforward, because there's no y's over there, so these are just derivatives like normal. And the next thing I want to point out to you guys is to get dy dx by itself. It comes down to one simple idea. Get all your dy dx's on one side, and then get everything else on the other. And in this case, since there's only one term that has dy dx, what we're going to do is just, who cares what it has in it? Who cares what it is? Just subtract it over to the other side. So 1 times y to the 9th, that's the same thing as just y to the 9th, right? So what we're going to do is say, we're going to subtract that over, no matter what it is. If it doesn't have a dy dx, it subtracts over. All right? So then that's going to leave us with 9xy to the 8th dy dx, which is equal to 19, which must be minus 7. There we go. 19 x to the 18th minus y to the 9th. Okay. Now that we got dy dx over here, let's go ahead and just, how do you get it by itself? Well, this stuff's multiplying, so we're going to go ahead and divide it. And I'm not going to show the step in between. I'm just going to do it. I hope you guys can follow along. So that's going to give us dy dx is equal to the stuff on the right, the 19 x to the 18th minus, that's the world's worst 18. Let's fix that up. There we go. Minus y to the 9th. All divided by, well, what was over here that we're dividing by? 9xy to the 8th, 9x times y to the 8th. And no matter how ugly it is, that is your answer. It does not matter. I hope that helps. I hope that's working. All right, so here we go. One more problem. Now you'll notice this one has quite a bit of space. So we're going to go ahead, and I want you to go ahead and look at this for a minute. Give it a pause, see how it goes, and then unpause the video and see if you did it the way I wanted you to do it. Okay, let's see how you did. All right, so this one, we have a product rule, so we're going to go ahead and say the derivative of x is 1, and then leave the y alone, plus, leave the x alone, derivative of y is dy dx. Okay, plus. Now that one looks easy, but I promise you that always gets students on the test, because it's always, since they're both to the power of 1, you forget, things go all crazy. So pay attention to that one. That one comes up a lot. All right, so now the next term, the y squared, the derivative of that is bring the 2 out to the front, subtract 1 from the exponent, times the derivative of the junk, derivative of y is dy dx, equals, derivative of 2x is 2, the derivative of negative 4y, well, 4 is a constant, it's going to, because it's multiplying y, it's going to stay there, derivative of y is dy dx. So now in this problem, you'll notice how many, there are 3 terms that have dy dx in it. So, as I said in the last problem, our goal is move all the dy dx's to one side, move all the other terms to the other side. So I'm going to move my dy dx's to the left, and then everything else to the right. So I'm going to add the 4 dy dx's over and subtract the y all in one step. So that should give me what? X dy dx plus 2y dy dx plus 4 dy dx is equal to 2 minus y. And just to help you see it, the y is right there. The 2 stayed on that side. It's still right there. And then you can see the 4 dy dx went right there. The 2 stayed on that side, stayed on that side. Okay, so I hope that helps. All right, so now what? Well, I got to solve for dy dx. And this is our first time seeing this, but hopefully it doesn't throw you off too much. Maybe you even saw it all on your own. So I'm solving for dy dx. Well, I have a dy dx in all these terms. And how do I solve? Well, this is very similar to like an old school problem, or maybe we had something like this. 3x plus, I don't know, let's say ax equals 7. I say solve for x. Well, you say both of these terms have x's. So we have to use the f word. We have to say factor out your x. There we go. And so you'd see now I have x by itself, so I'm able to divide by 3 plus a, right? So we're going to use the same idea here. Notice every term has a dy dx, and it will always be just a dy dx. It will never be raised to a power, which makes our life super nice. So now what we can do is just use the f word, factor out a dy dx, and what's left? X plus 2y plus 4. And then that's going to be equal to 2 minus y. And why I was emphasizing before, saying no matter how ugly it gets, we don't really care. Because all we're going to do is always, every single time, we're going to factor out our dy dx, and then no matter how ugly it gets, we're just going to divide by whatever's in this parenthesis. Whatever it is, we really don't care. It's just going to be our answer. So therefore, I now know dy dx is equal to 2 minus y over x plus 2y plus 4. All right, so that was a pretty good implicit differentiation problem. So if you got that, good for you. That's awesome. All right, they don't get much harder than that. Now, I wanted to show you guys one more case where implicit differentiation comes in, because how do I put it? The unfortunate side is nothing in math and nothing in calculus does just one thing, right? Right? There's always lots of uses. So for this one, what we're going to do is we're going to say, look, if I wanted to do the derivative of this, if I just did the derivative of one side, what on earth am I going to do with that? An x raised to the x. Holy cow. That seems hard, because what rule do I use? Is it a power rule? Well, because it's something raised to a power, but it's not. It's a variable up there. So is it an exponential rule? Well, no, because the x is in the base, so it looks like a power rule. You can't use either rule. It's both of them. So what we need to do is we're going to use logs. We're going to go ahead and use logs to figure out how to get through this. So we need to remember our log rules, and there's the 3 of them. I'll refresh them at the speed of light right now. Rule number 1 was if you have log base A of m plus n, let me make that a little bigger. Let me write a little bigger. All right, so if I have log base A of m times n, try again, there we go. Then that can be rewritten as log base A of m plus log base A of n. So saying no matter what the log's base is, just if the input, if it's multiplying, then I can break it up into 2 separate logs and have them adding. The other rule is very similar. If I have 2 things dividing, well, once again, I can break it up into 2 separate logs, and they are broken up into subtracting, right? And then the third rule, this one's really, really important, log base A of m raised to the n is the same thing as, well, what we can say is that exponent comes out to the front, leaving me with log base A of m, and then this whole thing is being multiplied by n. And MAT212, you can go back and review all that stuff, why it is, or I can throw videos your way if you really want a lesson on it to remember that. But those are your 3 rules. Hopefully that's enough of a refresher. Okay, so now let's go ahead and see how that applies to this. Well, right now, what's causing the problem is I have a variable raised to a variable. So what I can do is just do the log, take the log of both sides. I'll use natural log since it's easier to work with. And now what you can see is I now have natural log of x raised to the x. So what that does for me is using that log rule number 3, it says I can bring my exponent out to the front. So now I have the natural log of y, which is equal to x times the natural log of x. And now, once I have done that, how I've rewritten it, I am now able to do this derivative, am I not? Am I not? Let's do our derivative rules. What's the derivative of natural log? Well, that's 1 over the junk times the derivative of the junk. Well, the derivative of y is dy dx, all right, which is equal to, now, how do I do the derivative of this since I have 2 things multiplying? Product rule, right? So the derivative of x is 1, leave the natural log alone, plus, now leave the x alone, derivative of natural log is 1 over x, those divide, leave me with 1. So what does that do? What does that do? So that's going to leave us with 1 over y dy dx equals natural log of x plus 1. All right. So we're almost done. We almost have our derivative. We just have dy dx. It's not by itself. It's being multiplied by 1 over y. So, well, I can multiply both sides by y, right? And that gives me dy dx is equal to the natural log of x plus 1 times y. And it's very tempting to leave that y there, because in the other problems we were just leaving it. Well, why were we just leaving it? Well, the other problems, it was too hard to solve for y. That's why we were using implicit. We were using that first idea of when do you use implicit? Well, when it's just too hard to solve for y, it would just be too rough. Well, this problem, that's not the case. In fact, it started to solve for y. We know exactly what y is equal to. So it's important in this problem that we sub y back in. So I now know, all right, my answer is going to be dy dx, which is equal to the natural log of x plus 1 times x raised to the x. And there is my answer. So the next idea for using logs, using implicit, they go hand in hand with using logs to simplify things. So since we now know implicit, we now can look at this and say, well, I can't do that derivative, but if I take the log of it, I can bring that x up to the front, and now doing my derivative, just because I have a natural log, my y trapped inside of a natural log doesn't goof up my whole process. I can do this derivative just using implicit. So that's another powerful part of implicit. I will show you one other use of this real fast. It might be for something like this, where you might have, like, I don't know, x to the 4th raised to the 5th times x minus 3 raised to the 7th divided by x minus 2 raised to the 8th. Something like that. Okay, where this problem, you'd say, I can absolutely do this using quotient rule, and product rule, and chain rule, and oh my goodness, all these rules. But couldn't we do this a nicer way? Is there an easier way to do this? Well, using our log rules again, what I can do is say natural log of one side, natural log of the other side, right? Okay, so it's just going to take a second to write all this stuff down because there's a lot here. All right, now, what does my log rule say I can do with this? Well, since I have things multiplying in the numerator, I can break these up into separate logs and make them adding. The thing in the denominator, break that up into a separate log and make it subtracting. So what we're going to do is called expand the log. So this is going to be natural log of x minus 4 raised to the 5th plus the natural log of x minus 3 raised to the 7th minus the natural log of x minus 2 raised to the 8th. So now you can see it's already looking a little bit better. But I can clean this up even more because I can bring all these exponents out to the front, can't I? So that would give me natural log of y equals 5 times the natural log of x minus 4 plus 7 times the natural log of x minus 3 minus 8 times the natural log of x minus 2. Now, why is that actually helpful? Well, now if I do the derivative, these derivatives just became super simple. And the derivative of natural log, well, hey, that's just 1 over the junk, right? So here we go. This derivative, going up to here, the derivative would be 1 over y dy dx, because the derivative of y is dy dx. Now, here we go. 5 times, what's the derivative of natural log? 1 over the junk times the derivative of the junk. Well, what's the derivative of x minus 4? That's just 1. So that's easy. All right, plus 7 times 1 over the x minus 3 for the exact same derivative rule, and then minus 8 times 1 over x minus 2. All right, now what? We're almost done. Our derivative is all written on the page. We just got this 1 over y multiplying dy dx. So let's go ahead and multiply that to the other side. So it's going to give me dy dx equals 5 times 1 over x minus 4, plus 7 times 1 over x minus 3, minus 8 times 1 over x minus 2, all of that times y. And we're not quite done. Why are we not done? Stop and think. Oh yeah, we can't leave this equal to y. The only time you can, or with a y in it, the only time you could do that is when the problem started and it was so hard to solve for y, you just couldn't do it. Well, in this problem, once again, the problem I just wrote here, we started with it equal to y. We know what y is. Y is that whole thing. So we're going to go ahead and rewrite the problem one more time. dy dx is equal to all this stuff. I'm going to now multiply my 5 into the numerator. So it's 5 over x minus 4 plus 7 over x minus 3 minus 8 over x minus 2. And then y, we know, is x minus 4 raised to the 5th times x minus 3 raised to the 7th divided by x minus 2 raised to the 8th, the original problem we started with. And now we have our derivative. So there are, and I think for some of you who are comfortable with your log rules, you'll look at this and say, wow, that's way better than having to do quotient rule. Low d high minus the high d low all over the square of what's below. And that's significantly better because notice our high had a product rule and chain rules. And then it just would have been this gigantic, enormous mess where here you're like, look, it's a couple log rules. I'm good at those. I can do, break it up into 3 different logs, adding and subtracting, and it just kind of pounds itself out, not too hard. So I hope that helps. I hope I've given you a couple ideas on how you can use implicit, when you can use implicit. The next section is going to be called related rates. And related rates is, once again, using implicit. So we'll come back to this, okay? Give a few problems a try, and the trick is if you're going through the homework and you're trying to pick out what's the difference between related rates and implicit differentiation, related rates have context, okay? Related rates, we're going to, instead of be doing x's and y's, we're going to have other variables. So do a few problems that just have x's and y's in it, and then come back and watch the next video.